Thank you. So today I'll be talking about, like how non-convex problems abound in machine learning, but most of the times we cannot give any guarantees, right? If you do local search on a non-convex optimization, you get stuck in bad local optima. And so that's why, where, the biggest challenge is how to come up with the guaranteed solutions in that case. And so what I'll show is with this class of tensor factorization techniques, you can avoid bad local optima despite being a non-convex problem, and how we can apply tensor factorization in a range of different applications. And most recently, we've shown how to train neural networks using tensor methods. So this is joint work with two of my excellent graduate students, Majid Jansamin and Hani Sedki. Majid will be, in fact, on the academic job market, and he's excellent. So I hope, he gets a chance to interview in all these excellent places. So we know that learning with big data is, one of the most important challenges of current times. So what makes this hard? Right? The challenge is, as we have more and more data, the idea is this is noisy and messy data. We have all kinds of noise associated with the data, which makes information extraction hard. So learning with big data is literally like finding a needle in the haystack. And so in this high-dimensional regime, as I have more data, I also have lots of variables. Right? So, and this makes it challenging for learning in a computationally efficient way. If I want fast algorithms that can quickly process the data and find this needle in the haystack, that's a challenging problem. It's also challenging in a statistical manner, meaning like how many samples of this data do I need to see in order to find this useful information, right? What is the sample complexity of learning? That's again a challenging question. And so this is what makes learning with big data a challenging problem, both in the computational and the statistical sense. Right? So in terms of framing machine learning tasks, almost all machine learning tasks can be framed as optimization problems. Right? If you think about unsupervised learning, for instance, clustering, you can think about as optimizing for a modularity score, where you have similarity within the cluster and you minimize similarity across clusters, right? Or you can think about model-based learning. You have a probabilistic latent variable model, such as, say, a topic model, and you want to maximize the likelihood, of the data under that model, right? And of course, in the supervised setting, if you're training a neural network or a classifier, you want to minimize some kind of loss, usually a quadratic loss between the predicted output and the ground truth, right? So a lot of like machine learning problems can be cast as optimization, but the challenge is most of these optimization problems are non-convex, right? And in terms of our understanding of the theory behind non-convex optimization, it's really still in its infancy, right? So we have a very good understanding of convex methods, whereas non-convex methods are challenging, right? But on the other hand, real-world problems are non-convex, right? Literally, like the optimization landscape is like having lots of peaks and valleys, right? So you have this in a very high-dimensional space, and that's what makes it challenging. So I also want to point out there is an active Facebook page on where there's lots of discussion about non-convex optimization, and the latest papers are posted there. So I encourage you to subscribe to this page and keep up with the updates. And so contrasting convex and non-convex optimization, with convex optimization, we have one unique global optimal point. So if you run local search methods such as gradient descent, you're guaranteed of converging to this unique optimal point. And you can also bound the rate of convergence. Right? But on the other hand, with non-convex problems, you have multiple local optima. In fact, there's a curse of dimensionality that the number of stationary points can be exponential as you increase the dimensions. And this is what makes learning with big data even more challenging. Right? So how to deal with a high-dimensional non-convex problem and still have guarantees that I can get to a good solution, right? So how do I ensure that I can get a bound on the final solution that I'm going to obtain? And that's what we'd like to address. This is a very challenging problem. And so what I'll show is, this class of tensor methods has actually some nice algebraic structure that will ensure that there are no bad local optima. And now the question is, how are these methods applicable to different machine learning tasks? So today what I'll show is, specific to the problem of neural networks, we can cast it as a tensor factorization and obtain provable bounds, like obtain bounds on what the risk of the resulting network going to be. And this is what will allow us to overcome all the hardness of non-convex optimization. So we'll see how to go about specific to this neural networks. And if I have time, I'll talk about some of the other applications of tensors in terms of unsupervised learning. Most recently, we have a result on reinforcement learning of partially observable Markov decision processes. So there are a number of other scenarios where these tensor methods are applicable. But my focus will be on these neural networks. Right, so we're all aware, that neural networks has been extremely effective. Recently, deep learning has revolutionized computer vision and a number of other areas. But if we ask about the theory behind, why these methods are successful, or how can we in theory, where, what is backpropagation doing, right? That's a very challenging task. I mean, training these networks is a highly non-convex problem because you have these multiple layers and you're learning the weights of all these layers together. Right. So let me start with a simple toy example and ask the question, what happens to gradient descent or backpropagation in that case? Right. So I want to ask, in this example, can I, expect that there'll be only good local optima, or will there be a bad one? Right. So this will give an intuition of why it's so challenging to analyze backprop in high dimensions in large-scale problems. So the problem I'm considering is simple, just a two-dimensional input, right? You have this input x1 and x2, and it's a very simple classification problem. You have these positive clusters, right, with positive labels, and these green ones are the negative labels. And I'm training a network with 2 neurons to classify this. And now if I ask about what is the optimization landscape of this, right? So what are the local optima for this specific problem? It turns out, indeed, as you expect, there is a globally optimal solution. So there is a solution that would separate perfectly the positive clusters from the negative ones. Right, which, in this case, because it's separable, you expect this globally optimal solution. But it turns out that even in the simple case, it's a simple enough task, but it turns out there is also a local optimum. So there's a bad local optimum where the middle positive cluster is wrongly classified as the negative one. So if you initialize somewhere close to this solution, you would get stuck in this bad solution, right? And you can prove that this is a stable local optimum. So meaning it does have a basin of attraction. And so that's the problem. Like even in this simple example, right, a seemingly simple task, you already have the issue of a spurious local optimum. So if you think about visualizing the landscape. So here what we did was we fixed all the other parameters of the network except one of the weight vectors. So one of the incoming weights to the neurons, we wanted to plot that. And you can see the non-convexity here, right? The landscape is clearly non-convex. So in general, backprop will suffer from this bad local optima, which is not surprising because I said, non-convex optimization in general has an exponential number of stationary points, and there can be arbitrarily bad local optima. On the other hand, we've come up with a different objective function. So our algorithm will optimize on this objective function based on tensor factorization. And for that, we can prove that we'll go to a good solution. We'll in fact go to the globally optimal solution under a set of conditions. Right? And here I'm just plotting the objective function for our tensor objective function. And you can see that in this neighborhood, it's locally convex. So it doesn't have this problem of non-convexity of the backprop. And so that's the motivation. So backprop suffers from bad local optima. Can we come up with another alternate method of training that we can guarantee will go to a globally optimal solution and will get us a good neural network that's guaranteed to generalize well, right, onto test data. Right, so I'll just briefly describe some of the classical results on neural networks. So most of the theory of neural networks has focused on the so-called shallow network. So this is a two-layer network with one hidden layer in the middle, right? And it turns out that this is a universal approximator, right? So there are results by, Andrew Barron, Peter Bartlett, and others who've shown that you can bound what is the approximation error of a given neural network for approximating a certain class of functions. Right? And you can also bound the sample complexity of training such a network, assuming you have infinite amount of computation. Assuming you can get the globally optimal solution, there are guarantees of being able to train this with polynomial number of samples. Right? But the downside is, so far it's not clear what is a computationally efficient way of reaching these risk bounds. Right? And in terms of computational complexity, there are all kinds of negative results. Right? In fact, training a network with even a single hidden neuron is NP hard. Right? And this is what is like I said, most of the results are pessimistic. But why this doesn't stop us from pursuing the problem further is to ask, yes, indeed, there are hard instances, but what are the cases which are tractable, right? So with machine learning, it's not necessarily the worst case instance that we are after, right? Because machine learning may be the scenario where, we want to extract information from data and they may turn out to have conditions that are tractable, right? And so that's what we'd like to come from a different perspective and not consider all possible instances. And when it comes to guaranteed solutions for simple methods such as gradient descent, there are results only in some very limited scenarios. So if you think of a linear network, so if the layer of neurons is just a linear activation, right, then training a two-layer network is nothing but matrix factorization. So in this case, there's no spurious local optima, right? Because we know finding matrix factorization can be done efficiently, even though it's non-convex. And that was an observation made by Pierre Baldi and his student, right? But on the other hand, if there are nonlinear activations in general, there will be bad local optima for gradient descent, like the example I showed in the previous slides. And only in some very special cases you can give guarantees on being able to train a good network. So one of them is the special case of learning polynomial functions. So if my final target function is a polynomial of the input, it turns out that assuming random weights for the first layer suffices. So if you randomly draw Gaussian weights independent of the training samples, it turns out that's a good, that'll result in a good network. So in this case, just training the second layer of weights turns out to be a convex problem, so you can give guarantees. Right? But that's specific to the case of polynomials, and also under a special distribution, only under a Gaussian or product distribution of the input, this works. Right? So in general, this doesn't work. And another class of methods have been so-called improper learning scenario. So this is the setup where I'm allowed to expand my size of the network, right? Have a larger network, and be allowed to train in an incremental way. So meaning every time I'm adding a new neuron, and I can do this in a computationally efficient way if I have quadratic activations or more generally polynomial activation functions. On the other hand, if they are the standard sigmoidal units, which is the standard neural network, this is hard. Right? So you cannot do that with sigmoidal units. And so these results, kind of state that in most of the scenarios, like for general networks, so if I have a general input and general sigmoidal activations, it's hard to train a neural network. Right? So the question is, how do we overcome this hardness, and what are some new insights we can obtain, right? What are some new techniques we can bring in to give guarantees? So again, feel free to interrupt if there are questions. Only if they're linearly separable. So, so it's just like one line. So even the example that I showed was not linearly separable. So in all those cases, there can be bad local optima. So yeah, so gradient descent has no spurious local optima if it's linearly separable, which is right very, very limiting. Yeah. Yeah.
And your inputs are samples for the calcium.
Right.
Your training sample is sample calcium. Then random initialization is the first layer.
Yeah.
Followed by gradient descent type method.
Yeah, for the second, yeah, because it's convex, right? Once you fix the first layer.
We'll recover the polynomial.
Yeah, we'll fit the polynomial well. Yeah.
And the idea is that the polynomials are in the span of what the network can model.
Yeah, exactly. Yeah.
To the extent that, for example, the network doesn't have the polynomial you need, will be good in some sense of approximation sense, the nearest polynomial the network can build.
So not in general, right? I guess if it's only like some small deviation away from polynomial, you could still probably argue. But if the deviation is large.
Something like if, let's say, the actual function is some fourth order polynomial.
Yeah.
The network is more likely to will it be the best order of approximation?
Not in general. So yeah, it's like, unfortunately the greedy kind of like, approximation doesn't work. Yeah. No, not the layers, just the neurons. In the same layer, neurons one by one you're adding.
I see. Grow the network.
Exactly. And it's the improper learning scenario. So you could have a much larger network compared to the one you're initially going after, because you're adding one by one. But you can bound how much that is depending on exactly. Yeah. And again, like even like for adding one neuron, right? You can only solve the optimization problem exactly for the quadratic activation. And for higher order, it will be like kind of maximizing a tensor norm. But you can approximate it and argue that that's good enough. So that's the way they go about arguing it. Any other questions? So these are the results so far. So, so what kind of new algorithms can we bring in for training? So the insight we have is, indeed, there are hard instances for training neural networks. But suppose I tell you about the input distribution, does it make things easier, right? Does it make the task easier? I mean, in general, if I know, like, say, the shapes of, say, for instance, the different clusters in this input instance, does that give me a better handle on training neural networks? Does that help me overcome the problem of, bad local optima in my optimization? How do I use that information? Right? So this is the classical debate between generative models and discriminative models. Right? In the generative models, you're not only modeling the mapping between the input and output, but you're also modeling the input distribution itself. On the other hand, neural network is a discriminative framework where you're only modeling the conditional distribution of the output given the input. Right? And now the question is, if in addition, I tell you information about the input distribution, does that also help me in training a better neural network? Does that help me guarantee good training of a neural network? And that's what we'd like to ask in this. That's what differentiates our work from the other works on training neural networks. So what we'll assume...
You mean class conditional distribution, not in the previous picture, you don't mean that all the dots are on the same color.
Yeah. But only, it'll be just the model of the input, right? So it won't need any labels. So it's unsupervised learning.
So if you go back to the
Yeah.
slide,
Yeah.
you could say all these could be the same color. I don't
Right.
need them to be
Right. So it doesn't matter what the labels are. So essentially, I want to ask. I'm going to tell you what the shape of the input distribution is, and how does that affect training, right? I mean, it could even be the regression setting, right?
picture on the left example, I thought you were talking about very something about class conditional distribution, but no, it's the same.
No, I'm just saying this is the joint distribution I'm modeling here.
Basically, it's a mixture, and you're
Yeah.
assuming that the mixture components correspond to class segment.
Need not be, right? So, I mean, I have arbitrary model of the input. I mean, it could even be the regression settings. So I have some arbitrary model of the input. And then I want to model the conditional distribution. So I want to...
Maybe precise what you're
Right.
doing.
Right. But the whole idea is I want to also worry about the input model itself for training a neural network. And that's what will show will overcome the hardness of training. That's the key. So from now on, I'll assume that I know the input distribution. In practice, I can, estimate it using a number of unsupervised techniques. I could do spectral methods. Some of my earlier work was to show how tensor factorization can solve for learning the model for a whole range of distributions. It could be score matching. So there's a whole range of unsupervised learning techniques. So we'll assume we know the input distribution and ask how that will be helpful for training the conditional model, right? For training the neural network that maps the input to the output. Right? So that'll be the, we'll show how that overcomes the hardness of training. Yeah.
Well, so here you say the neural network is extremely efficient matching.
Yeah.
But as far as I know, like the different species of posing matrices that can be modeled.
Yeah, but that's not the same as the supervised setting, right? That's the unsupervised one.
Does the method apply to that kind of model?
No, we are assuming the supervised setting here. So you have the input and output, right? And then you have this, you want to...
That model is can also channel supervised phase, right?
Sure, you can have like a reconstruction error or some notion, but we'll start with assumption we know the input model, right? So it's not really applicable for that setting because there you're trying to learn the input model using the Boltzmann machine. Whereas we assume that there is a pre-trained input model that I know the parameters of, and I'm going to use that input knowledge. Right, so that's the setting we are interested in. No, only the input distribution, right? I mean, if I know the joint distribution, I'm done. So I'm only going to assume about the input distribution, and the argument is I can learn this in an unsupervised way. Usually, I have a lot more unlabeled samples, and I want to transfer that knowledge for training my neural network.
I must say I'm curious to hear your results. So what you're telling me is I'm going to learn a function, and the only additional knowledge I'm assuming is I'm going to tell you which part of the domain is actually useful of this function. You're saying that the input is within this subset of the domain.
Right, or the shape, right? Yeah.
It's a distribution.
Right.
So my first
Precisely.
conclusion is it shouldn't be helpful at all.
Will. So now I'll tell you how precisely good. Okay. What do you think? What do others think? Okay, so we have both opinions, so we'll see what happens. Right? So yeah, the question in general, it's challenging to ask how to use that knowledge. So the way we go about this is to say, whenever I want to train a neural network, right, the mapping between the input and output, are there some transformations of the input? So for instance, if I compute these functions phi of x, and can that result in a better training algorithm? So I'm transforming the input and using that in my training method. And so how could I use this transformed input? The idea is I can form different kinds of moments between the input and output, right? And that's where these spectral methods come in. So for instance, I can compute very simple moments. I can just look at the cross correlation between my input and output. Or I can look at higher order moments of my input correlated with the output. Right? So I can come up with this whole hierarchy of moments relating the input and output. But what we'll show are these class of moments that have a transformed input will be very useful for training a neural network. And these class of transformations will depend on the input distribution. So this is where the knowledge of the input distribution will be useful. So the idea is, depending on what the input distribution is, you need a different transformation, and you need to see the relationship of the transformed input with the output to learn about the weights of the neural network. And that's kind of the overall idea, right? So you can see how this is different from the backprop objective. So here I'm going to try and fit these moments and ask, can I invert the moments to find the parameters of that model? And that involves two aspects. One is identifiability, right? The moment I'm considering, does it have enough information about the parameters of my model? And the second is computational tractability. In a computationally efficient way, can I invert the moments and get the parameters? Right? So I need to address both these questions. Right? And what makes it challenging in the scenario of neural networks is there's this middle layer of nonlinear activations. Right? So if you consider simple moments such as just the input and the label, just these kind of cross moments, in general, they wouldn't have a nice relationship with the parameters because of all the nonlinearities. And the main insight is, if we instead consider these transformed inputs, we can overcome that. But finding those transformations will require the knowledge of the input distribution. And that's how we exploit the knowledge of the input distribution in our framework. So now we'll see what class of these transformations, these functions phi of x, will be useful for revealing the parameters of my model, right? In this case, the weights of my network. Right? And so this is where we'll also need the methodology of tensors. So if I want to represent pairwise moments, I can do that with a matrix, right? Correlations, I can use a matrix. But now if I need higher order moments, I need a tensor. Right? So for a matrix, I can, I'm just going to introduce this outer product notation. So if I want to find the cross correlation between, say, these entries I1 and I2, I can, collect in the matrix the correlation between them, right? So this is how I index all the correlations between my indices. And this extends to tensors in a straightforward way. Similarly, I can collect all the cross correlations, triplet correlations between the variables at hand. Right? So this way now I can build a hierarchy of progressively higher order moments and ask what kind of information it reveals about the underlying network parameters. And so that's why tensors are needed, because we need progressively higher order moments with more information about good network. So now we'll see, we'll go back to the question of what class of transformations are going to be useful. As I said, the class of transformations will depend on the input distribution. So what is the insight? What are the class of transformations that will be useful? Yeah.
So what we're getting at is that if I was looking at the real joint distribution of xy, in principle I could recover it from, if I was given all moments of xy together, or any order that I want, they will completely specify the joint distribution. So from those I can recover the joint distribution, and then I'm home.
Yeah.
So what you're saying is that even if I don't have a lot of labeled data, just the unlabeled data will give me constraints on this joint moment.
Right. That's the insight. That's a very crucial insight. And so I don't have to go to high order moments. And on the other hand, at the same time, I want to do it in a computationally efficient way. It'll give me equations on the moments that are computationally tractable for me to recover the parameters. Right. Yeah. And that's why this class of transformations is crucial. And now, what are these class of transformations? So we'll start with this notion of score function. So it's very simple. So you take the p of x, the input PDF, and you take the log of it and take the derivative, right, with a negative sign. So the insight is, just this toy example, if you have a Swiss roll as your support for the input density, right, and if I plot the score function, it's a vector field. And the intuition is like where my input distribution is changing a lot, then I have a larger value of my score there. And score functions have been used in statistics before. In fact, that's the underlying basis for the Stein's method. And all this it's mostly used in the context of Gaussian distribution. There's the James Stein's shrinkage estimator. And so this has been in literature before, right? But this by itself does not suffice for us, because what it does is, if I have a vector input, it transforms it into another vector. On the other hand, I said I want a hierarchy of moments, right? I want progressively higher order moments. I want matrices and tensors and so on. So this is why I need the extension of this notion. So we'll naturally look at higher order moments of my input distribution. So I'm going to look at higher order normalized derivatives of the input density. And this way now I get scores that are higher order tensors. Right? So with second order score, I have a matrix. With the third order score, I have a tensor, and so on. So this now gives me a hierarchy of moments with increasing order of the tensor. Right? And intuitively, it's kind of looking at also the higher order variations in my input distribution. And so there's more information about the input that I'm using by way of the derivatives. And that's what we will use in our framework. So that's the question. Now, I introduce these core functions, and as I said before, what we are going to do is we'll find the cross correlation between my output label y and the score functions of the input. Right? And indeed, to find these core functions, you need to know the input model. That's how we use the knowledge about the input distribution to compute these core functions. And then using labeled samples, I can find an empirical estimate of this moment, which involves the label and also the score function. And now the question is precisely this. What information does this moment have? Right? Can I characterize what the information captured by this moment? And this is where, this was our first, result, which showed that in any general scenario, what it will reveal are essentially derivatives of my label function. So this f of x is my target function, right? This is the function I want to estimate. This is nothing but the expected value of the label given my input. So if it's a binary label, it's just nothing but the probability of a positive label. Right? And that's the function I want to estimate with my neural network. That's my target. And so what we show is, if you compute this cross moment, right, this left-hand side is something you can estimate with data. Right? It's equivalent to this right-hand side, which is equal to the derivatives of my label function, but there is expectation over the input. Because,
just to make sure
yeah.
So in that cross moment UFX cross S, what you're going to do is you're going to use all the unlabeled data to actually figure out the function S.
That's right.
And once you have that, you still need your labeled XY
Exactly.
to estimate that.
To estimate this cross moment. And that's why this is supervised.
S, which would otherwise be horribly complex.
Right.
You can get that.
You can get that with the input model, and you can plug in, what you think is. Exactly. For instance, for Gaussian or mixtures of Gaussian, this would be nothing but just the tensorization of the input, right? So you kind of have this nice progression of higher order moments. Yeah. And so that's the idea, like we can find these moments with labeled samples, but what is it equivalent to? So our target is ultimately to estimate this function f of x. right? Although we can't have full access to that, what we show is we'll get access to the derivatives of the function, but I'm going to average over the input distribution. So this is a general result. It requires very mild assumptions. I think an important one is that the PDF should vanish at the boundaries, which I think is a very reasonable one. And so now the question is, in the context of neural networks, what does this yield? Right. So
at this point, I don't even use neural networks. I just say do some regression with some sparsity and differentiation.
yeah, but the main challenge is this, right? The main challenge is this: there is expectation over the input density. So in general, you wouldn't get access to the pointwise derivatives, like pointwise access to derivatives, because in the end, I want to estimate this function pointwise, and that's why for a general framework, this is challenging. But now, why it is good for neural networks, training a neural networks. We'll see neural networks have a special structure that will help me yield the parameters despite having this expectation over the input distribution. And so let's consider this, the classical neural network. And we'll first assume the realizable setting, meaning we'll assume that the function is exactly generated by this neural network. And we'll show, in the next coming results that, in fact, we can relax this. Like, we can also allow for some approximation error. But for now, assume that this function has been generated from this neural network, right? And here you have arbitrary sigmoidal units in the first layer, and then the second layer is just a linear combination, right? So that's why I can write this as this inner product, because it's a linear combination of the outputs of the first layer of neurons. And now I'm going to ask, suppose I have function structured in this way. Can I apply the previous result, right? Can I apply this form of the derivatives and ask how it relates to the underlying parameters of my network model? Right, so I can compute the derivatives. That's straightforward. Right, so let's go about and compute that and see what that yields. Right, so this was the result. We said we can compute the quantity on the left-hand side. We can compute the moment between the label and the score functions of the input. And as I said, it will yield me derivatives of the label function, right? Here now the function is of this form, and I can take the expectation over the input. So let us compute the first derivative, right? So this is now nothing but the first derivative of this function, and you can see that it's essentially a linear combination of generalized linear functions, right? Each sigmoidal unit is a generalized linear model, because it's doing a linear transformation and then a nonlinearity on top of that. And so you can model the, and so the derivative of that would bring out the weight vectors here. And then you're taking linear combination, and that's why this is a linear combination of the weight vectors. So the idea is each weight vector corresponds to the set of weights that come into a neuron, and now I'm taking a linear combination of them. So if I computed the first order moment, this is the information I would be getting. Right, I would be getting linear combinations of the weights of the first layer. And we know that this is not sufficient for learning, right? I'm just getting one vector that's a sum of all these vectors that I'm after, right? I want to estimate all these vectors here in order to learn the network. And that's why we need to go to higher order moments. So now I can ask and compute the, right? So this was the first order. Now I can go and compute the second order moment. So again, because of the structure that it's an element-wise neuron operation, the second order moment also has a nice form. It turns out that it's sum of rank 1 components, and each rank 1 component corresponds to one of the weight vectors. So now, is this sufficient for me to recover the network? What do you think? Right, so I'm giving you a matrix where which I'm expressing as sum of rank 1 components, and each one corresponds to one of the weight vectors. So can I recover these weight vectors from this matrix? right, up to like a linear transformation, right? Because I can only recover the subspace because I, don't have enough constraints, right? Because I know like matrix decomposition, I can only do up to an orthogonal representation. And in general, the weights need not be orthogonal. And in fact, if the number of neurons is more than the dimension, right, I have essentially recovered nothing. And that's why I need higher order moments, right? That's why I need tensors. And so now I can ask about third order moment. And you can progressively keep writing this higher order moments for the neural network of this kind. It has a nice structural form. So it's again sum of rank 1 components, and each rank 1 component corresponds to one of the weight vectors of the first layer. Right? And now I can ask the same question, can I recover this decomposition uniquely? And it turns out the answer is yes for a class of tensor problems. And so that's the benefit of going to tensors. You can recover even a non-orthogonal representation under some very simple set of conditions from the tensor, but not from a matrix. And even say if the number of neurons is larger than the dimension, I can progressively keep going to higher order moment and ensure that I have enough constraints to recover the weight vectors. And so that's the main difference from the usual backprop method. So what we are going to do is recover first layer of weights with this tensor decomposition, and then we'll recover, for this network, we wanted to find like an end-to-end guaranteed solution. So it turns out there's a simple Fourier technique, a technique in the Fourier domain to recover the other parameters of this model. And so that's what we used in this setup to recover the other parameters. So essentially the biases and the weights of the second layer. So what we have is an end-to-end framework for learning all the parameters of this two-layer network. Right? So the idea is we start with the input and do unsupervised learning and obtain this class of score functions. So these are normalized derivatives of my input density, and I'm going to compute this based on whatever the input model I have. Or I could also do this in a non-parametric manner. Arthur Gretton and others have recently shown that you can get like good rates for non-parametric score matching techniques as well. So you can compute these score functions, and once you have them with label samples, I can compute the cross moment between my labels and the score functions of the input, right? And I need at least the third order tensor, as I said, to recover the parameters. So I'm going to do the third order one. And then I will find a decomposition of these components and find the components of the tensor, and that will give me the weights of the first layer. And the other parameters are recovered through a simple Fourier analysis. So that's the overall framework for this algorithm. So as I said, like the others are recovered through this Fourier analysis. So the main, like what the tensor decomposition will give us are the weights of the first layer. So you have the weights here of the first layer. And the second layer can be recovered after that. So there is A2 will be, so this lambda will be dependent on A2 and also the sigmoidal function we are considering. So it'll only come up in this way, in the scaling and not in terms of the decomposition. Then it'll change. So, in general, then it won't be a linear combination here anymore. Right? Because Y is a linear combination, we are getting this linear combination here. And so, so more generally, if I have many layers, there's going to be more distortion of these forms. And so in some limited cases, we could still use these structural equations. But it's going to be, like there's going to be distortion of that. Yeah. Yeah, so in general, that's hard, but in our previous work, we had this set of conditions. So essentially, if the factors are linearly independent, We can orthogonalize them through simple procedure called whitening. And then the orthogonal tensor decomposition, you can do a power method iteration and be guaranteed to get to a good solution. Be guaranteed to get to the globally optimal decomposition. And that's the, and
But isn't it the case that because the electrical side is completed only when it goes to then the electrical
So-
side will not complete and start to
right. I mean, so it's all, I mean, so this analysis also handles perturbation, right? And that's the subtle part of it. Like how much of perturbation can I handle and still be able to guarantee solution? And we have bounds on, yeah, it will. It is, and we are still able to guarantee what the resulting solution is, because the idea is, in the exact case we know we'll go to the globally optimal solution. Even in the approximate case, as long as the perturbation is small enough, we show that we can recover it with the same bounded error. And that's the subtle part of the analysis. The perturbation cannot be too large. As long as it's within the bound, we can handle it.
The other question is, as you pointed out, when the number of intermediate layers is large,
Yeah.
the solutions from the first and second order moments are unique. Are you saying that from third order moments is unique, or are you saying that you use the calculation of
Right.
several order moments?
I mean,
and after what order do you get?
I mean, in general, you would need higher order moments, right? So it depends again on the class of like weights. So in our recent cold paper, what we showed was if the weights are incoherent with one another, so meaning they're not too correlated, you can also just do just with third order. So you don't need to go to higher order. But in general, if that's not the case, then you would need to go to higher order. So there is like, yes, you can bound like essentially like if k is like of the order of d to the say p by 2, then that's the order I need to go to. Like so that's a rough bound, but it could be better than that. P would be the order of this tensor. So the order that I need to go to should be the one that scales in this way. Like k is the number of neurons, t is the input dimension. And so there's a bound, but it could be better than that. No, yeah, but you would, I mean, but we also know information theoretically we need, that many parameters in some sense, right? So, and yes, for computational you need a bit more. So, it's like, yes, there is a gap between the information theoretic and computational. But yeah, there is a trade-off, of course, of asking for computation as well. And so I think since we are running out of time, I'll just very quickly, say that in the manuscript we have the details. So we can bound what is the how many number of samples we need to estimate this function efficiently in the realizable case. And as I said, like the details of the tensor decomposition method itself, like what are the conditions under which it succeeds and what level of perturbation it handles, were there in many of our previous works. So I encourage you to look into those results. And so I want to quickly cover is the non-realizable case, right? In general, we don't have a neural network generating the target function. So in this case, how do I still find a good approximation to my network? And this is where we'll, to my function. So this is where we'll use the classical result by Andrew Barron, who related the approximation error to the Fourier spectrum of the function. So the idea is if the function is smooth enough, meaning the higher frequencies of the Fourier spectrum are bounded, then the approximation error is small. So if the network has k neurons, it scales as 1 over root k, the error in my approximation. Right? So this is the bias. So in addition to the error because of limited number of samples, I also have this approximation error. And there's also a nice insight on what is the neural network that has this good approximation error, right? The bound that I just showed. So it turns out that if I just sample from these weighted Fourier spectrum, right? So I draw samples from this distribution, normalized form of this distribution, and set them as weights for the first layer. That has a good approximation error. So using this insight, we can extend our results to now the general setting. And what we show is as long as the approximation error is small, which would be the case when CF is small, right? So CF was this smoothness constraint on the function. So when CF is small compared to the size of network that I'm constructing, then we can have an overall bound on the risk of my estimation of the function, right? So this involves now both the error due to limited number of training samples, right? The n is the number of samples, as well as the approximation introduced by the fact that the target function is not within the class of neural network functions. And the limitation of why we can only handle functions where the approximation error is small, again, comes from the fact that tensor perturbation, we can only guarantee up to some bound, right? If the tensor is perturbed by a large amount, there can be hard instances because we know the general tensor decomposition is hard. And that's the reason to have this limitation. And so the message is as long as the error of approximation of my target function is small enough, when I look at the class of neural networks I want to use, I can guarantee a good training with this method.
It's very clear that the error goes down with the number of errors and the number of samples. Can you comment on the effect of D?
So the effect of D is implicit through the CF, I guess, right? So in general, this could be exponential, but then you could have smooth functions where this is much better. And so that's the idea. Instead of it being an explicit bound, it's implicit through the CF in the approximation error.
Generally, what I was sort of asking is, are the chances of F for the CF with D, or is it increasing?
I guess all realistic cases are all increasing, but how fast it is, right? The worst case is exponential. But for instance, if it's a Gaussian function, it's only like root D, I think, and like polynomials are like linear in D, and depends on the number of monomials. So you can come up with it. No, but so the thing is like it's really the comparison of D and K, right? The idea is you also need to be K to be large enough. And with images, we have additional constraints actually, because it's a convolutional model, there is the tying of the weights. So it's kind of, even though the ambient dimension may look large, but because of those constraints, right, it's actually a lower dimensional problem. So that's the additional aspect as well. Right, so that's the overall. Yeah. Right. That's right. High frequencies. Yeah. It could be exponential in general. Like the worst case is exponential. It does get worse with dimension, right? In the worst case, it's exponential in dimension. So. Yeah. And especially with images, the convolution will really result in more constraints. And in fact, in a different work, what we've shown is you can also incorporate convolutional constraints into this tensor decomposition. So if I'm like solving for convolutional models, and we have shown that that can also help in avoiding bad local optima. And since I think I'm out of time, I'll stop here. I'll just comment that the main ingredients we used was the model of the input, like imposing probabilistic models on the input and using that information from unsupervised learning for supervised tasks. We were able to overcome hardness of training, right, and have computationally efficient ways to train neural networks. And the main methodology we used was tensor factorization. So the idea is, although tensor factorization is a non-convex problem, we can characterize the optimization landscape and show that under some simple conditions, you would get the globally optimal solution. You would get the best decomposition. And I didn't give much details about the tensor decomposition, but we have a series of works where we've characterized what these class of conditions are, how much perturbation can these methods handle, and what's the convergence rate, and what are the class of techniques to do this. So I can talk to you offline if there are more questions on that. Thank you.
Faculty will be following the questions that we continue to make a case for why they're here. Phil, there is a question.
Yeah.
So for the, I think this is related to the method that you use. Do you use joint diagonalization method?
So, again, joint diagonalization in the non-orthogonal case can be quite tricky. So what we do is not that we first orthogonalize the tensor, and then there is a power method, essentially an extension of the matrix power method to the tensor case. So we use that method. But yeah, there are a number of other possibilities. We could also use alternating least squares method. And for the convolutional setting, that's the method we used. And while we do the alternating least squares, we're also projecting onto the space of circular matrices to incorporate the convolution constraints. Yeah, so there are different possible methods, again, we could use. And yes, simultaneous diagonalization is one of them. One of the challenges we've found with that is when you take random slices of the tensor, there's information loss, right? There may not be good eigenset gap in those slices. And that's one of the challenges with that method. And you need many slices for that, and it's unclear what the trade-off is. Yeah.
So in the typical case these days, we have 3x3 handles.
Yeah.
So in that case, the DP is only that.
Right.
So
Right.
that's actually good.
Right. Yeah, so even if you have the light, it's really the size of the filter that matters. Yeah.
So in the high-level space, for the non-convex problems, why do we care about the global optima? Because I really want papers from the other to see, and that paper is talking about the people network may have a set of local minimum which is close to the global optima.
Are you talking about the paper about the random spin glass?
No, it's about the law surface of the...
Yeah, that is based on this random spin glass model, right? I think the issue I have is the random spin glass is really, according to me, very far from the multi-layer neural network. The approximations they make are quite strong. They assume essentially I think every path in the network is essentially the same, and there are a number of assumptions I think that are to me quite far from the actual one. We still don't know whether there are bad local optima. You saw even a simple toy example, there is a bad local optimum. So yeah, so it's unclear. With in the high dimensional setting, there is explosion of stationary points, right? The question is how many of them are bad local optima and how many of them are reasonable. That's a very challenging problem. So I don't have an answer for that.
But the paper is referencing how many of those stationary points are saddle points and not local points.
So I think what they were saying was there's this band, what they were arguing was, for that random spin glass model, all the local optima are concentrated in a band around the global one. That's what the random spin glass theory says. But in my view, the neural network is far from a random spin glass. So that's the issue I have. Right? The physics model is not what's captured. I think it's not capturing a neural network very precisely. That's my issue. But there's also another paper, I think, by Yoshua Benjiu and also Surya Ganguly and others have also argued that saddle points are the real issue, and that's correct. Saddle points are an issue, and even for tensor problems, there are exponential number of saddle points. But it turns out because we understand the overall landscape well, we can avoid them in polynomial time. We can guarantee that we won't run into them. And so it's a special class of instances where that's possible. And more generally, yes, it's interesting to ask how to avoid saddle points. I was talking to Daniel earlier about that. And so, yeah, it is an issue for general non-convex methods. Yeah.
I have a question which is based on possibly a wrong understanding, but I'll tell you. So what I understood is that if you have a lot of unlabeled data, you can do a tensor factorization, and what that really does is it gives you a representation. It says, take your data and represent it this way in terms of these tensor factors. And then the next layer is really going to learn the function. Is that a good understanding?
That's right. So, I mean, so what we did was more of you could use any method for input models, but if you use tensor factorization, the idea is, yes, you're learning a representation from these higher order relationships just in the input, and you transfer that, and then the rest is figured out after that. So
that's good then, because the real learning is happening in the E of x.
Exactly.
So y times E of x.
That's right. That's right.
So if I have enough unlabeled data that I can, let's say, go ahead and do the first layer, does that then tell me where to get labels? I'm asking a very pragmatic question.
That's more like the active learning setting.
Not so much active learning. I just want to know how to sample. In other words, do I really have to do just random sampling, or can I do some smart sampling for labeling purposes?
I see.
I'm not thinking active learning in the sense of now that I've learned a few, what do I do next? I'm just saying a priori.
I see. Even offline,
even as I have an issue, I can get unlabeled data, do whatever I want with it, and then I have to start paying once I have.
That's right. So it's essentially like you want to query at the places where the input is changing fast, right? There is enough gradient in the input.
You're talking about
density of the input. So there is change in the density of the input, because the score functions are only
first order, it's not just the log likelihood. You're thinking also.
I mean, the higher order moments of it. I mean, essentially, but if it's some nice model, it would have derivatives, so essentially you want them not to be zero, right? So not stationary point.
It's a mixture of Gaussians. You don't want the peaks, you don't want the valleys.
Yeah, somewhere in between. Yeah, and so I was talking to Percy Liang. He pointed out how kind of this idea that dropout kind of shrinks the margin and. For training, and the idea is for us as well, a smaller margin is better because then you're capturing the gradients better. And so that's what I think differs from other methods from more on separability. This is not based on separability. Yeah, good. So we've done it on MNIST, and we have reasonable results without much tuning, and essentially increasing the rank of the tensor leads to a good number. I think so without much tuning we got I think up to 98%. But in order to I think go to other data sets, we want to ask challenging scenarios. I think first of all, the convolutional, the CNN setting, we already have great results. So instead of competing for that, we want to look at other scenarios, maybe the recurrent neural network scenario, which is now challenging for training. So we're now started exploring that setup and ask how these methods can make a difference there. But that's in the supervised setup. But in the unsupervised scenario, we've done a number of different frameworks for topic modeling, for extracting hidden communities from graphs, and there compared to variational techniques, we get a huge speed up, more than 100 times speed up in running time, because we can use all efficient matrix libraries for computing these tensor-based operations compared to the variational inference, and so that's where we've seen a lot of gains, and we hope to also you have that in the supervised setting as well. So we are pretty fast. So again, as I said, these tensor methods are fast, and so we haven't compared again side by side. I mean, we felt like MNIST, doing a detailed analysis was, I think, not something. That would be very impactful. But that's why we want to move to the RNN scenario and ask all these questions there. But we do, I mean, I don't think the time would be our bottleneck. The question is really the quality of the solutions, right? The gradient descent and other methods versus ours, which one is better? Yeah.
So, I guess for all language people sometimes like for us, X is a string. Score function isn't
Right. And so that's what,
really help us, right?
I mean, unless, like, again, you can assume a model, right? You could think of a simple hidden Markov model. I mean, if you're directly trying to predict using HMMs, it's quite weak because of it's a linear model, right? But you could now use that to just like find these core functions and just some representation and transfer this for training a recurrent neural network or some kind of another sequence model on with nonlinearity.
About, like, the assumption that we had, like, the gradient of X with respect to X of log of X.
Yeah, so
Function, right? X for us is not a.
no, understand when it's a sequence, you can again impose an input model, right? I'm saying a simple model would be a hidden Markov model on the input. So you can do unsupervised learning and fit the input to a hidden Markov model. And now once I have a parametric model based on the hidden Markov model, I can use that to find the score functions.
Okay.
And then I can transfer it. And that was what I was also, talking to Kevin earlier. So hidden Markov model by itself may be weak for prediction, but I'm using that only to transfer information from unsupervised to supervised. So that could give good gains. No, but we are not, in the sense we are using it only in a weak way, right? In the sense we are using that only to extract features that we think will be related to the label, and then we are, again, doing feature extraction at the next level as well. So it would be better than just using solely those features for classification. We are not limiting to that. And so that's why I think it could, it would only probably help but not hurt in doing that. Any other questions?
No more questions. I want to answer my own question. And so initially I thought that if I just want to learn a function,
Yeah.
and all they're going to tell me is how the inputs to the function are distributed, why should it help me at all in learning the function? It's just something about the input. But I guess what you're telling me is that knowing how the input is distributed can help you sort of unwarp, project up, that you basically change the input space in such a way that now it's a function from a new domain to the
Exactly.
domain, and somehow that function has been made easier to learn.
Exactly. So in a sense, what we are saying is, if you look at the transformed input, it will have more information about the function you want to estimate, and depending on what the input distribution is, that function will change. Yeah.
So what example do you look at, like classes where sort of associated with peak and density? You have multiple labels at a density.
That's fine. So that's what this method kind of really does not assume, and it could be the regression setting, right? I talked about learning polynomials, so it really is not based on separability, and so that's the other strength of these methods as well. It's not one of like how separable it is, which a lot of data won't be separable. So I think that's the strength as well. All right. Thank you.